Okay. Mm-hmm. Oh, I have too much fun with my job. Let's talk about these troubleshooting methods. I just printed off a bunch of new lab packets. I went through and corrected the errors on these. So for instance, like on lab 1, it used to say CR1, it's supposed to say MS1. There was no overload, normally closed on there. Lab 2 and 3, I believe. Remember the pilot lights used to be in series with the overload, the neutral did, and I ran those straight across. So they're a little more proper. So if you want to use these new ones, there's a bunch of new copies right there. What else? Systems troubleshooting. So this is one of the PDFs that you're going to use for your homework. And let me pull up, let's see. You download, bitch. There you go. Oh boy. Use that one though. 3. Looky there. How many of you done the systems troubleshooting homework? Wait a minute, was that due today? Oh, I hope you did it. Recall seeing the 4 troubleshooting methods in there. This is all good information, but it's, I don't know. I only ever feel the need to cover these troubleshooting methods because at least it's something for you to get in the habit of doing, especially when you're troubleshooting a ladder diagram. But these methods are good, not just for ladder diagram troubleshooting, but also in any application really, even small electronic components. There's 4 methods though: symptom and cause, output back, half split method, and shotgun method. Let me cover the first one, the worst one first. The worst is first. Shotgun method. And I hope I don't see any of you doing this, but I see it. I used to see it in the field a lot, and I do see it in the classroom too. Let's jump down to shotgun method real quick. Where's it at? Shotgun method. In the shotgun method of troubleshooting, the troubleshooter tests every component or connection in a suspect area. The shotgun method can save time if there are only a few components to test or the problem is intermittent. However, usually the worst method to use will be the slowest if the circuit is large. And man, I saw this so much in the field working with certain people, but here's the shotgun method, my humble opinion. Volts. Okay, we got a problem. Ready? Let's see. That we got nothing there. We got this there. and there's nothing, well, let's try this. Yeah, that's okay. No, there's no rhyme or reason. You see what I'm saying? There's no method. It's just like, hey, we got voltage, we don't got voltage. It's people will jump in there with their meter and just start checking shit. And it pisses me off because there's no, like, what are you doing? Like, what are you looking for? There's no methodology to it. So don't do the shotgun method. The two that work kind of hand in hand, which is what I would recommend you get in the habit of doing. And there's no set in stone, step-by-step deal. It's what do you see? Like, where do you think the problem is? And what do you think the cause is? So symptom cause and output back. These are the two that I would recommend you get in the habit of kind of having a mindset towards. So symptom cause method is you're working in the field and it's either a customer or somebody in the plant or a friend gives you this and they said, here's the problem. You need to know what the symptom is. You can't be handed this thing and say, go to work. You're talking to people, whoever gave you the issue to work on, whether it's your boss, a friend, a customer, whoever, yourself. You got to know what the symptom is. So in this whole thing, this is a pretty simple process, right? I mean, this one I believe is set up for lab 3 because I see some limit switches hooked up, but I don't think it's done. Anyway, you got to have an idea of what the process is that you're trying to do. So if you look at the print, what is this thing trying to do?
Turn on a motor or reverse.
Yeah. Yeah, it's one motor. You got the ability to run it clockwise or counterclockwise. I mean, it says frickin' garage door up there, but that motor's going to go in a certain direction until this limit switch is opened. And then it's going to go the other direction until this limit switch is opened. So in a moment, I'm going to put a fault in it and we're going to troubleshoot it. And we'll see what the symptom is first, and then we'll try to determine what the cause is. Output back. These kind of work hand in hand. So how many outputs do you see on this ladder diagram?
Output 3.
I see 5. So whether you're looking at an electromechanical ladder diagram like this, or a ladder for PLC logic, and some of you are taking PLCs now, a lot of you will take it the second 8 weeks. No matter what, you're trying to get continuity, either electrical continuity or logic continuity from left to right, right? Remember this? And then usually all of your outputs or your loads are going to be on the right, and all your inputs or your, I don't know, pilot devices or switches are going to be on the left. So here's what I see. I see you got a motor, you got a forward relay coil or motor starter coil, you got a green light, you got a red light, and you got a yellow light. So if the symptom is that the motor is not going in the forward direction, where do you think you would start? What's the output back that you think you would start with? Correct. Why wouldn't you look at the motor? That's an output. The motor's not running in the forward direction.
Presumably it's running in reverse though. So
right. It's working counterclockwise, but it's not working clockwise. The only thing that has to do with are these contacts. And what are these contacts controlled by? The coil. Yep. So if you started with the motor and started to work your way back, eventually you would end up at this coil not closing anyway. Well, let's say you go press that forward button and the light turns on and this pulls in. So your output, this forward coil is actually good. That pulled in, but it's still not running in the forward direction. What's the problem? So timeout. So you're saying this doesn't work?
They don't run in the right direction, so you say?
What?
You say they don't, you turn it on, but they don't run in the right direction?
Yep. I give you this print and I say, hey, the motor's spinning in reverse, but it's not spinning forward. Can you fix that for me?
Yeah, this cable is the wiring is wrong.
The wiring is wrong. Yep. A plus. Where?
And motor wiring.
The motor windings?
Yeah.
In here?
And to turn the motor backwards or forwards, you have to switch the cables are free, right?
Yes. And where does that happen at?
What happens? It happens right there.
Yes, sir. Okay. So let's back up a little bit. We just determined as a class that the output we're looking at is this forward coil. The symptom is that the motor's not running in forward. The cause we're trying to figure out, but before we even put a meter on this thing, we've already dialed down where the problem should be, where we expect it to be, because we press this button and this coil pulls in, right? So if that coil is pulled in, do you have voltage there?
Yeah.
Yep, sure do. You got current going through it. Everything's working fine on that contactor, which means these should be closing. So then where would you check? You could, but if it's me, I'm sticking on that that motor starter somewhere. Remember, these overloads are up here. So on your print, I press the forward button. I see that this thing pulls in, right? So those contacts. What do you mean by electricity?
Current through the.
Yeah, current through them. So if it's me, I'm going to look at that forward motor starter and check voltage on the line side and the load side of this, of these contacts, right? So I should get 208 going from here up to the overloads and then down to the motor. If I have them, let's say I've got, I'm going to start checking voltage now. I got my meter, okay? My meter's out. And I'm looking in this area right yonder. On that motor starter contactor, I'm going to check the line side and the load side of these contacts. So when I put the positive lead somewhere and I put the negative lead somewhere on the line side, let's say positive here, the negative side, I need to find a good 2 or neutral. The other day, I don't remember who, but at least 1 or 2 of you were checking voltage in the power circuit to this 2. And that's no good. Why? Well, you got 2 separate systems here, right? You got a power circuit and control circuit. You got a 3-phase 208 on the top, and you got single phase 120 down here. So this is single phase.
There's no voltage on the ground.
120. Well, remember, ground, your negative lead is going to whatever reference point you're checking to. You're looking for a difference of potential between 2 places. And at any given time in this process, when this whole thing is running, you should know where you should have a difference of potential. And it's not even shown on this print, but do you remember how I had you guys, or showed you guys to take this, remember the little neutral on the front of the disconnect? In front of the disconnect, you got L1, L2, L3, and then it says N, neutral. I told you guys we need to take that and reference it to ground, right? So this is going to be your best reference for potential for your negative lead in the power circuit. And then this guy, you might say, well, hang on, I'll get to that. This guy is going to be your best reference of potential for any of the control circuit wiring, right? Because let's say this wire is not in there. If I check three-phase 208 voltage on one leg, I should have 120 to ground or 120 to neutral. Where I'm getting that neutral or ground from, though, matters. If I get it from down here, I might get some weird readings, right? Anyway, I'll back up. What are we doing? Checking the line side stuff. Okay. So I'm going to put that neutral in here. And I'm going to check from this point to here. And let's say I'm reading 120. So let me show you what that is. So from this neutral over here, disconnect to this is 120. And then I go to L2. And this is 120. And this is 120. And just to double check, if I went from L1 to L2 on the same side, what should I have? 208. So 208, 208, 208, and each of them to ground should be 120. So I got 120, 120, 120 on top. Well, let's say I got 120, 120, and like 19 here. Is 19 a usable voltage? No, you're catching some kind of stray transient voltage or some induction from something that's giving you a reading. But this is no dice. So what do you think the problem is there? Basically on this, it's jumbled for good mess. But this is this L3 right here is a normally open contact, and when the contactor coil pulls in, it should close, right?
Yeah.
So I got 120 volts on top, and with it closed, I've got nothing on the bottom, basically, which means this thing is either not closing or the contacts themselves inside this contactor are dirty, or they've been arcing and they're not making good contact, right? Okay. Another example that would be like output back. Be what if symptom is it's not running in the reverse direction. It's running in the forward, but not the reverse direction. What's our output?
If they don't run in a reverse direction, that means the connection between the forward relay and the reverse relay. There don't be a connection between those two.
Up here?
Yeah.
Could be. But what if I told you that contactor is pulling in?
So
What if I told you the yellow light is turning on?
Okay. Well, that means the phase, the connection between phases.
Maybe, but you're kind of shotgunning a little bit. You're looking at it saying, well, this could be wrong, this could be wrong, this could be wrong, this could be wrong. But let's have some methodology to it. Let's say, what is our output? And then work our way back towards the source. working in the forward direction, not working in the reverse direction. Is our output that we need to check the motor? No, you could start there, but you'd be wasting your time. The output would be this reverse thing. But I'm telling you, okay, that's not pulling in and the yellow light is not turning on. So we got no output there. We got no output there. Output back means you start here and you work your way back. So what's the first thing that you're going to check voltage on? No, the coil. Now you could look at it and you would probably be right if you went to the limit switch. Right. You could look at it and you would probably be right. But there is a chance that you would have voltage here and have voltage here and nothing's working, which means your yellow lights probably burn out and your the coil on the reverse side of that contactor is open or
What
not
you
working.
mean is like don't trust it, even if we see like the light is off, still don't trust it, check for voltage in there.
Yeah.
So even if I know the control light is not working, but the light is off, you know, if I see those two, I'm gonna go for go check for a switch, for a limit switch. Like, what do you mean is, like, don't trust him, let's check him out before I go for the limit switch?
Yeah.
What you mean?
Yep.
Okay.
Okay, so we're going to go output back, and output back means from that output away from the output and towards the source. I'm not getting any voltage. What am I doing? Oh. Okay. So 0 volts, 0 volts. And as I'm checking these, where's my 2? Where's my black lead from my meter? What am I referencing to? So I got my positive lead from my meter on the load side of the line side of the coil. Where's my other lead? Yeah, this is the best 2 of this whole system, because that's the 2 from the source. Coming from the source, our transformer is our 120 volt single phase source, right? Now, could you check to this too? Yeah, you could check to all this stuff. But if you got a break right here in this wire, you're gonna get really confused. So I guess what I'm trying to say is, since our transformer is sitting right there, the best source for your 2 or your negative lead is gonna be right here on this X3. Make sense? All right, back to voltages. I got 0 volts, 0 volts. Where's the next place I'm looking? Heath said it already.
You have 0 volts on the limit switch?
Mm-hmm.
Or you check the unit for the limit switch? The other side?
0 volts.
Yeah, check the other side.
And then I'm checking here. 0 volts, 0 volts. 120. Oh, look, on the line side, I got 120. What's the problem?
You got an open relay? Or
The interlock itself is not closed, most likely. So how do we check that? Because from there, we're not done. We can't walk away. And in real life, you find this problem, what's the next thing you do? This is real life stuff. Do you just replace it?
no, you have
No.
to check the works or not, or the opens and close or not.
Right. You have to check continuity across it.
Yeah.
You suspect that forward interlock, normally closed, which is this guy down here, you suspect that thing is open for some reason. It's failed.
Those are usually mechanically connected, aren't they?
Yeah, so the interlock up here is 21 and 22. And this contactor's right here. It's this contact right here. So this is a normally closed contact. There's a screw on top and there's a screw back here, right? So there's a wire going to it and underneath it. This is the interlocker, normally closed auxiliary contact attached to this coil. So when that goes in, this should open up. This is out, it should be closed, but I just found no voltage here and voltage here. So I suspect that this is actually open. Now in the field, remember, labor costs a lot of money. Whether it's your money paying for yourself to do this job, or you're working for somebody, like you're really smart now because you've gone to ICC, you've worked with this idiot and grandpa, and you're worth a lot of money now. So it's going to cost a lot of money for you to flip it. What's going on with this thing? Am I?
Zach, that's a good action shot.
Yeah. Look at that. I'm thinking you could sell that for art.
You're really thinking.
But like you can tell I'm thinking, but like I'm getting it. You know what I mean? Like look at my eyes. I'm getting it.
Hey, that's the best thing. The best picture so far.
I'm getting it, man. I just need to unplug this one. It's getting confused. She gone. Okay, so we're 99% sure this is the problem. M-Daddy said it, we need to isolate this and check it because we would be bad electricians if we pulled this whole thing off, unwired everything, maybe even marked them to see what was what, pulled that thing off and put it back on, and we were wrong. It could have been just maybe this wire going there was a little loose, right? So what we need to do is isolate it. And real life would, so we just isolated on this trainer, and now we're going to check continuity across that. Real life is you pull these wires off and put your leads on there to check continuity and push that coil in. When I do this, I should hear beep, right? So I'm suspecting that we would go like this and not hear anything. Then you know, okay, there's something going on with this contact. Pull this thing off or pull that contact off, get a part number and replace it, okay? But you see how the output back thing works? You might think, well, that I could probably get to that without doing that whole methodology stuff.
The pushing button.
You might be right, but let me show you something. When you get to the drill station, here's your ladder diagram. Page 1, page 2, page 3, page 4, page 5. Holy smokes. What you're going to find on this thing, which this is the last ladder diagram thing in this class you'll troubleshoot, is that you're going to need to find an output. Okay, the clamp is not retracting. Here's a clamp retract rung or group of rungs. The output here that we would suspect is this solenoid, that's a symbol for a solenoid, is not energizing. So we're checking voltage here and then here, and we're going to keep going. And what you're going to find is that, okay, CR2, this contact does not have voltage on it, but it's not closed, and it should be. So where's CR22 on this thing? Then you got to go find CR22. Maybe it's up here. And then you start working your way back there. So why isn't this coil closing? Work your way back. You might get to something else that doesn't have voltage in it, should, because it's not closed. Then you got to go down here and find this. So to just suspect, even on these more simple prints, that, well, I can look at that right now and say it's the forward coil or the forward interlock. Just take the time to go to your output and work your way back on the print. You're going to be a lot better off in the long run. You get in the habit of doing that, and you will be a good troubleshooter. the last method that I want to show you, and then I will we'll do an example, is what was the last one? Half split. Somebody meant, I think, mentioned half split the other day. I think Will did.
Yeah.
Are you awake? What are you looking at? What are you staring at? What are you doing? Are you TikToking? I want to see. What are you doing? You on Facebook?
No.
No. Just messing. What?
Last time I've been on Facebook was last month.
Really?
Yeah.
Where are you at, half split? There you are. Half split says, okay, you got a ladder diagram. This one's only 5 rungs long. You got a problem with the entire system. You start checking voltage in the middle. What do you think is wrong with that? Basically, the idea is I'm going to cut this ladder diagram in half, check some voltage, and then I will know if the problem is on the line side of where I'm checking, so rungs 1 and 2, or the load side, rungs 4 and 5. What do you think the problem with that is?
If there's no power on 1 and 2.
The problem is most more complex ladder diagrams are not sequential like that. You know, this CR1 might energize rung 86's contact, and then a timing relay in series with that might energize another relay coil that's back on rung 3. So if your system is sequential, like, okay, rungs 1 and 2 have to be turned on before rungs 3 and 4 are. Rungs 3 and 4 need to be energized before rung 5 is. Then you could do that. But this example, and I just showed you what you're gonna see this too. You might find the output that is the coolant. The coolant's not turning on. Okay, let's check this motor starter. CR13, oh, we got a problem here. This CR12 is not closed, and it should be. So where's CR12? It is on page 2, and we were just on page 8. So to go to the middle page here, the middle set of rungs, check a voltage somewhere in here, and then decide that the problem is either on the line side or the load side of that somewhere is just wrong. There's too many jumping around places in that process. But here's where half split method really comes into handy. I've used it a lot in lighting circuit troubleshooting. For instance, I'm gonna draw a big old long circuit of lights here. Doesn't even have to be lights, it could be outlets. But somewhere in this here system, let's say this is 277 volt. So L1, neutral, and this is 277 AC. Somewhere in here, on L1, you're going to have a fuse or a circuit breaker, are you not, to protect all this wire? So let's say this thing is on a 30 amp fuse. And you're given this problem to troubleshoot. That fuse keeps blowing. What do we do? Why, first of all, why would that fuse blow? There's a ground fault somewhere, right? On the line side, there's a ground fault somewhere. Correct? The neutral is tied to ground. And if this spot right here, for whatever reason, a wire's pinched, some mice are chewing on the wire, and it's touching something metal, this is grounded, causing this fuse to blow. Does everybody understand how that happens? And why that fuse would be blowing right now? You're providing 277 volts through that fuse, trying to feed all these lights, but right here, there's a leak to ground. Something is grounded that shouldn't be. So is there anything stopping current flow? Are there any lights in there? No. So you're direct shorting this to ground because of this ground fault. Okay? So there's nothing limiting current there. It's causing the fuse to blow. Anything over 30 amps will cause that fuse to blow. So somewhere in this system, there's a ground fault that looks like that. How do we know where? Think about the output back thing. You got a lot of outputs there to work your way back from. Where do you start?
Well, we start with this light. Check.
Start with the last one? Did you say start with the last one or the first one?
The last one.
So what are you doing there? Well, you get into this light fixture or light pole or whatever it is. What do you do there?
I connect my I check the continue the finish. Line 1 to line 3 or line 2.
No. That you can check that and that's fine, but that's not going to show you where the ground fault is, right? Somewhere in this line of shit up here, something is leaking to ground. It could be here. It could be here. So do you start with the first one or the last one? You could guess. You could be right the first time or not. You actually start in the middle. What were you going to say, Heath?
I was gonna say, if you're using a half split, if you do in the middle and you can't find the problem, everything past it obviously doesn't.
Mm-hmm. You come to the middle, and this could be in a room full of lights, or it could be out. I saw it a lot. I use this a lot. I used to work outside a lot in highway lighting. The light poles are 200-300 feet apart, right? So it's not like I can just, move my ladder over to this one. It takes you a little bit to get to the next one, right? So if I start at the first one, disconnect everything after it, and turn it back on, and the fuse doesn't blow, I know that the problem is this way, right? So I disconnected this, and just fed that first light. Turn it on, fuse doesn't blow. I know the problem is somewhere down there. If I got lucky, the fuse did blow, and I know the problem is right here somewhere. But half split is you cut this thing in half. So you go to the middle, you open this up. So you're either at this light or you're at this light, and you disconnect the second half of the circuit. At that point, you can either turn the system back on, or you can use what's called a megger to test both directions to see if you have a ground fault. But we haven't talked about the Megger yet. We'll get to that when we do motor troubleshooting. But in this scenario, if I've disconnected the first set from the second set and I turn it back on and the fuse blows again, this went whoop. Where's the problem?
The first four.
In the first four. So you've just taken 8 and you've cut it in half. Okay. And that's the idea. Okay. So now I know the problem is here somewhere. There's a ground fault in here. Now what do I do?
Half again.
Go to half again. You disconnect this and this, and I turn it back on and the fuse stays. Fuse stays put, we're good. So running just these 2 lights, we're good. We've determined that these are probably good, but we know we've narrowed it down to somewhere in here, right? And at that point, you can do them one at a time. It just saves you a lot of time in the long run with something that's a circuit like this, to cut it in half. Then you narrow the problem down, and think about like a house. Think about a house. You could have the same problem with a circuit with outlets on it, right? So you might have this room, that room. This is pretty big, but let's say you got 10 outlets on a circuit, and they're in this room and that room, and it's tripping the breakers, and you don't know where. You know, you can get an idea of what circuit that breaker was on by testing these outlets and saying, okay, I got 10 outlets here that aren't on because that breaker is off. So starting from where your panel's at, if the panel's mounted here, you go to somewhere in the middle of it, disconnect that circuit, open it up, and turn the breaker back on and see if it trips again. If it does, you know you're somewhere from the halfway point back towards the panel. Does that make sense? So that's the half split method. Okay, let's do this. Let's do an example or two, walk through it together. And these are examples that you will maybe similar to ones that you're going to get out there, but not the same, because I'm mean like that. You guys know what these are called? These kind of twist lock. So you put it in there, and you twist it, and it locks. So it won't pull apart unless you untwist it. Okay. That comes in handy when this thing is hanging from the ceiling and you plug it in. That thing could just fall out, right? Unless you twist it. All right. I don't know who wired this up, but we're gonna see how they did. Whoa! Forward, reverse, no dice. Oh, this shit ain't good. Son of a bitch. Close your eyes and find your happy place and don't look what I'm doing. Find your fucking happy place. What are you doing? Close your eyes. Okay. Open them. Oh, damn. Oh, damn. No motor. Nothing's happening. Where should we start?
Putting the cable you put up.
Hmm?
I'm doing what you did.
Undoing what I did? Oh, unfaulting it? We could do that.
Could you start on the forward motor coil or which?
Well, neither of them are working, right?
Yeah.
Would it be, look at the stop button? That's open.
Yeah, but that's really not an output. So you could start there, but it's kind of random, right? So neither of these are pulling in, right? The motor's not turning on, but that's not the output we're looking at because neither coil is turning on. So if it's me, I'm just picking one. You're right. So, well, okay, let's go down that road. Neither of these are turning on, correct? So if a problem is here, it's most likely up here too. If that's the case, these are identical until you get to somewhere in here. More specifically, here. Okay, Heath's right. Let's start at the stop button. By the book, we would check the coil, then the limit switch, then the blah, 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 blah. But the only thing that's in series with all of that, because Heath's so smart, is the stop button. So let's check there. Maybe I should just shut up and let you guys do it. Why is this? What the?
Could that be the problem?
Well, it was working before I put a fault on. Okay, so you want me to check the stop button? Where do you want me to check?
Well, you want to check the stop button, you check from the line you are, from the beginning of the stop button to the line to ground.
I still like the idea of working from the right to the left. So if it's me, I'm starting on the load side of the stop button. And so, okay, here, and then where else?
The reference to ground.
It's free.
It's 3. Nothing. By the way, I just want to throw this out there. I should have voltage here, right? Let's say that I did. If I plug 1 lead of my meter into here and touch that, I'm going to get bit, right? If there's voltage on here, because your meter is just like another wire in the circuit. You're paralleling your meter with this point to see if there's a difference of potential there. So, and I've seen that a lot, but a good practice would be to go to your neutral first, because it's reference to ground, and then there. If I touch this, I'm okay. I don't want to, because I never want to just be careless like that. But this is reference to ground. I'm grounded, and I'm not a good current path. So if I touch that, I would be okay. But I just want to put that out there in case you didn't know. If I put 1 lead on something hot, this is now energized. Cool.
Start from the from the ground.
Yeah, it's a good habit to get into. Okay, I'm going to check that point. So I'm going to go 2 first. So this isn't sticking out there. Okay. I got nothing. Now what do I check?
Oh, well, you don't get nothing between the stop button and output.
Do you see my meter? Can you see my meter?
Yes.
I got 0.
Check the line side.
Good idea. Nope. Nothing.
So no energy is getting to the stop.
There's no difference of potential at the stop button.
So it might be.
So I checked here, got 0. Here, I got 0.
Okay, go
Now where should I go? So my other lead is right here. back to the source. So 2, I'm just checking the transformer itself. So this is X1. No dice.
No, guys, okay, so check.
Ooh.
So now we check the other side of the transformer.
Check the line side of the transformer. What should I see?
You should see 208.
208. Oh, I got 208 there.
You got 208 there?
Yeah.
Okay. That means the transformer is. Okay.
Sure.
Wouldn't you have to check the continuity to make sure it's bad?
Yeah, you would. That'd be the next thing we do. Yeah. So you're saying the transformer itself is bad. Which side of it?
The one with the low side.
Secondary side?
Yeah.
Okay. Let's check it. So check it for continuity.
Yeah.
Right, this winding on this side of the transformer, that's all just one big
Yes.
wire in a circle, round and round, and then it comes back out, right? So it should have continuity there. What did freaking beep like that? Ooh, the secondary side is good.
So we have ground.
So we know it works, but how it works, what is going to do.
So we
Well,
got ground.
we know we have 208 coming here. In other words, you got 208 here. You don't have 120 there. You got absolutely not 208.
Check that wire.
Maybe we could check the primary side. If we got good voltage coming to it and this coil was bad, if we got good voltage coming through it and this coil is bad, if we check that for continuity.
Yep.
You want to?
What's the worst that could happen?
So if I check the whole entire thing, I should have continuity.
Yes.
I don't. Oh, I have it from. Make you see that. Checking from 4 to 2, I've got continuity, but from 4 to 1, I don't. So there is a break in that winding, that coil between H1 and H2. So the problem here is the primary coil on the transformer is open between 1 and 4. So then you're okay to pull that thing off and replace it.
The whole unit, or do you replace just the individual coil?
It depends on the transformer, but especially for something that small, it's probably more cost effective to just
So like-
replace the whole
So I
thing.
assume like an IUC, since those aren't really fixed, we just throw the whole thing out.
Yeah, yeah.
Something does.
Most transformers probably don't even have the ability to rewind them because they're like molded cased. But if there's a really big, really expensive one, it might be looking into taking it somewhere. It might be cheaper to have somebody rewind it than to just replace it. All right, I want to do one more. Okay, go to your happy place for a second. You fucker. You looked.
I didn't see nothing behind the board.
I'm totally kidding.
I was in my happy place.
You go. Okay. Your happy place was staring at me. That's what you're trying to
that's
say.
exactly what I'm saying.
That's the same for a lot of people.
This is Zoom.
Okay. Oh damn. Oh damn. Oh damn. Oh damn. All right. Should we start at the same place since we have the same symptom?
We got the same
Let me start the wires then. Transformers.
That'd be a good idea. Still the same thing. Nothing. Where should we start? Huh?
Forward coiling,
Yeah.
start there to see what happens.
Yeah, but like Heath said, everything in this area is common to both coils. So it would be worth, in that case, jumping ahead to what's in series with all of that.
So low side push button.
So stop. Yeah, we'll start with the stop push button.
Is it okay to start from line 1 to line 2? Making sure you, like, instead of start from the 4 coil, we start from line 1 to line 2?
Right here?
Yeah.
Yeah, that's okay. I really like, I'm not gonna dock you any points for doing it any way different than me. I mean, you're gonna find your own groove. I'm just trying to teach you what's worked well for me in the field, time saving, cost saving. So no, is there anything wrong with checking the freaking disconnect right now?
Yeah.
There's nothing wrong with that because everything's right in front of you. But what if the symptom, okay, the motor and the contactor are in this room. What if the push buttons are in the next room? What if the transformer is outside on the other side of the parking lot? What if the disconnect is over by Ameren's poles? You know what I mean? So yeah, there's nothing wrong with doing that here, but you might want to, in the field, have a plan. That's the difference between us and people that shotgun shit. We have a plan, right? They're just like, oh, maybe I'll run over there and check that, and blah, blah, blah. They waste all day. Well,
So let's say if we had a big thing like that with a whole circuit all over it.
mm-hmm.
So if nothing's working at all, would you just go to the place that you're nearest to, see if there's even current there, for continuity, and then you can think about how the circuit would be laid out and work from there, or?
Yeah. There's a lot of variables to it though, okay? So what if, well, Zach's output back method told me to check in that cabinet over there on this motor starter coil. But the stop push button is right in front of you and it's already open. Might as well just put your meter leads on. It's a lot of common sense, you know, like just use your heads. But yeah, you're right. You can do whatever you want. Eventually you'll get to the problem.
When it's super big, think about the distance when you're troubleshooting and.
Just take a second and think about it. You know, that's all I'm saying. A lot of people are like, show up with their meter and, oh, that's the problem, boss. Okay. Like, take a second. Okay, so here's the system. What's the most logical place to start here? Sometimes I had a guy that used to say this to me all the time when I was apprentice. Slow is smooth, smooth is fast. Because I was that guy. I wanted to get in there and do a good job. You know, I wanted to impress people and be really smart. And what I end up doing is fumble fucking over all sorts of shit and taking wires off and making a mess. And if you take a second and think logically, what's the best? Is there a chance that right in front of me, this thing that's already opened up could be a problem? I might as well just check it. You know, and then what's the next logical thing to look at? But I can tell you all the methodology in the world. The more you do it, the better you're going to be at it. Okay, so what did we decide we're going to check here?
Load side push button.
Yep. So I'm checking the 2. I'm going to go load side of the stop push button. That's continuity. Nothing. Should I check the line side? Yeah. Nothing. What should I check now?
You check the line side?
Yeah.
What do you check?
Got 0.
Okay, when you go back to the
Load side.
Transformer. Load side of transformer. Nothing.
You're not gonna go side of the front, or we go the other side of the truck.
Okay.
Is that the problem? Should it be the problem?
No, I'm just confused why I'm getting a little jump in voltage. Okay, so nothing on the low side, or the line side. So X1, or H1 and H2 have basically 0 volts going to them. So you look at the power circuit.
We check the fuses.
Let's check the fuses first, right? Keep working your way back. So load side of the fuses. Huh! Nothing. Should I check the line side of the fuses? 208.
One of the fuses. They want the fuses.
One of the fuses is busted.
So check continuity, figure out what's wrong.
Yeah. Do you think we could do that without isolating them?
Yeah, we're there.
In other words, from this point to the neutral or the ground coming from your source. So from here to this neutral that's not on the print, what should I have? I checked and I have 208 here and I got nothing here. But if I have 120 there, should I be good? From there to there? Yep. From there to there, I should have 120. From there to there, I should have 120. From there, blah, 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 right?
What happens if I just hold the fuses and check the continuity?
And you're probably going to find a problem. I just want to show you things with meters so you see. So coming in, 120 on that fuse, 120 on that fuse, 120 on that fuse, 120 on that fuse. What? 120 on that. What? 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 Why would that be?
We have that connection.
I got 120 from each point to here. But I don't have 208 coming out of here. I got 208 coming in, but I don't have 208
Okay.
out of there.
We have that connection between fuse 1 and fuse 2.
Could that be a bad thing?
No, it's still a bad fuse, but I want us to figure out why we would still be reading 120 volts on each one.
Oh, why?
Because here's the thing, I've seen students bypass this and not be able to figure it out because they're just checking for 120 volts. They didn't check for 208.
Because
They went 120, 120, 120, 120. Oh, those fuses are good. But I got 208 here and I don't have 208 there. Why?
Because when you check the continuity, when you check the voltage between fuse 1 or fuse 2, whatever fuse is bad, they use the continuity from another side of the line.
I think what you're saying is right. What's happening here is, let's look at F7, if that's blown. So imagine that's open, there's no F7 there. If I check 120, or check this to neutral, I get 120 volts. Check that, I should have 120 volts. That
Yeah.
I should. Then you're reading back through the transformer,
Yeah.
you're still getting 120 volts right there, right?
Yeah. Mhm.
So just be cognizant of that. Like sometimes you're going to be reading things, and you'll be reading it back fed through the system, which is why you always, when okay, this is a problem, isolate it and check it again, right? Because I might be reading continuity.
And that's because the fuses don't have no polarities, right?
Okay, here's a perfect example. I think this auxiliary contact is not closing, but I leave the wires on and I check it for continuity and I get beep. Why? If this is not closing when it should be, why am I getting continuity right here?
Well, because the door or advance is pushed.
This is pushed? Nope, it's got nothing to do with that. You can take this button and throw it out the window and you can still get continuity right here. Why? Well, look at it the other way. Is any of this open? Through that coil, through that, through that, through that?
Yeah.
Right now, with that de-energized, I would read continuity across that. Right? Backfed through the entire thing. All of this stuff is closed. A transformer secondary winding is just a winding of wire. Right? So I would read continuity across that. Going that way. Which is why you always isolate it. You know, take the wires off and check it. Cool. I think I've talked that too long enough. All right. Monday we're going to go over the watch tank trainer. I was going to do that today and try to get it on camera for the people that aren't here, but I can't fit the damn thing in the door, so I'm just going to wait till Monday. Eric, Heath, and Ethan have dibs on 3 of the trainers. I'm going to go ahead and move this out to the lab so somebody else can work on it up there. So there should be 5 total, so there's 2 left for somebody to take up. And there's plenty of code homework and other shit you can work ahead on. You can work on your transducer stuff. If you got stuff to work on, I can help you with that. Your day, folks. Let's make it a good day. Bring it in.
See you on Thursday.
Team. Somebody needs to turn some music out there on too.